Hello everyone, my name is Jacob Adamczyk, and I'm an applied physics PhD student from the University of Massachusetts, Boston. Today I'll be discussing my research on maximum entropy reinforcement learning and its connection to non-equilibrium statistical mechanics. First, we'll define reinforcement learning as well as its generalization, MaxEnt reinforcement learning. Then we'll look at the statistical mechanics of trajectories induced by the MaxEnt RL problem, as well as a linearized solution for RL. Then we'll look at insights from linear algebra, specifically Perron-Frobenius theory, in order to approximate and bound solutions to the MaxEnt RL problem. Then we'll look at the connection to thermodynamics and statistical mechanics for MaxEnt RL. First, we'll define reinforcement learning. This is a paradigm of machine learning where an agent would like to take particular actions in an environment so as to maximize the total rewards accumulated. Each time the agent takes an action, it transitions to a new state S prime, governed by its transition function, and picks up a reward along the way, as governed by its reward function. The agent starts with some prior policy, which here we take to be uniform, and it's simply a distribution over actions for each state. By solving the reinforcement learning problem, we would like to find an optimal policy. An optimal policy is one where the agent taking these actions described by this policy should achieve the maximal rewards possible. Trajectories tau are denoted by consecutive states and actions for some given time frame, from 1 to t here. In maximum entropy RL, we append this extra entropic cost term, which is the cost due to the change from a prior policy π0 into a new current policy π. This difference between policies is measured with the KL divergence between these two distributions. Notice that in the large beta limit, this entropic cost is negligible and we recover the standard RL problem. At smaller finite betas, we get an optimal solution which is robust, meaning that the new optimal policy in MaxEnt RL is robust to perturbations in the rewards and dynamics. We'll study this problem of MaxEnt RL in the framework of statistical mechanics. It has been shown that if we define the probability of optimality for a certain particular state and action in this way, then at the end, when we use this optimality variable for the entire trajectory, we will recover the maximum entropy regularization term that we've seen previously. This means that by using this definition of optimality, we are indeed solving the MaxEnt RL problem for these distributions over trajectories. Now, looking at the probability of optimality for an entire trajectory, we notice that the denominator represents a partition function, and through statistical mechanics, we define a free energy in the following way. Now, using the definition of the optimal soft Q function from MaxEnt RL, we notice a striking similarity to the free energy in the previous slide. In fact, we find that the soft Q function is simply the negative of the free energy. Therefore, we're motivated to attack this MaxEnt RL problem by finding this free energy from a physics perspective. Now we define state action pairs I and J so that we can write down the Markov chain for state action pairs. This gives us a transition matrix PJI defined by the problem's dynamics as well as the prior policy. Then we can tilt the matrix with this exponential tilting factor based on the rewards, which will allow us to condition for optimality as we've discussed previously. Now, optimality for a path from I to J in n steps is simply p tilde to the nth power element ji. And now since we don't care about where we land in this trajectory, we're going to sum over all the nth or landing sites j, and that is precisely the probability of optimality for a trajectory starting with state I. In the large n limit, p tilde to the nth power is well approximated by the rank 1 contribution that dominates. Since our matrix obeys Perron-Frobenius theory, this is well approximated by its dominant eigenvalue to the nth power times ui vj, which are the dominant or Perron left and right eigenvectors. Since our matrix is substochastic, we write rho as e to the minus theta for some positive theta. Now, here we illustrate that the power method can be used to find the dominant eigenvector for our matrix by successively multiplying p tilde by some arbitrary non-orthogonal vector. We also note that this solution has geometric convergence with ratio dependent on the subdominant eigenvalue. This is related to the mixing time of the Markov chain. With the dominant eigenspace calculated based on the power method or some other method, we now have the solution to the MaxEnt RL problem. This means we can find the optimal policy, the average reward, which we note is equal to theta, which we will now call a bulk free energy contribution, and an optimal value function, steady state distribution as well. Steady state distribution is typically difficult to find in MaxEnt RL, but in our framework, we simply note it's the Hadamard product of left and right eigenvectors. So next, I'll show how the power method can be applied to some maze. So this maze is defined with some dynamics, which shows how this agent can transition from one state to the next, and then a reward function, which is everywhere minus 1 except for the goal state down here. This has a reward of 0, which is the maximal reward in this case. So by calculating the twisted matrix from the dynamics and the reward function, we can take successive iterations. By doing this, we're approximating the dominant left eigenvector, which we know to be the optimal policy. For some finite temperature, beta equal to 20, we have a somewhat greedy and still somewhat explorative policy here. So we notice after several iterations have occurred, we start to converge on a solution. And in some areas, we notice that there are still probabilities of taking, say, left or right actions. That would allow us to maneuver around this wall, which in the standard RL case would not be possible. In the standard RL case, we would only have one choice being accessible. This flexibility allows for robustness of this MaxEnt solution. Furthermore, the power method can be storage efficient because the dynamics are often very sparse. It will give us both the left eigenvector and the dominant eigenvalue, which are both important to MaxEnt RL. And finally, the power method is guaranteed to converge, since our matrix P tilde will have a positive, strictly positive left eigenvector. So now that we've seen how the power method can be used, we'd like to possibly get some bounds and approximations on the dominant eigenvalue and dominant eigenvector without having to do lengthy calculations or these heavy matrix multiplications. So as more information is known about the matrix P tilde, specifically the dynamics and the rewards, we can recover better bounds for the dominant eigenvalue and the dominant eigenvector. So with the dominant eigenvalue, we're taking row sums and column sums of this P tilde matrix to get better and better bounds. For the eigenvector, we need some more information since this is not a scalar component. So for this construction here, all we need is a lower bound on the matrix P tilde and an upper bound on the dominant eigenvalue. With that information, we can construct an element-wise max and min for our left eigenvector by inverting this matrix. Or if we know the entire matrix P tilde rather than some bounds, we can also generate upper bounds on each component of the left eigenvector. When we change the temperature parameter in the MaxEnt RL problem, we can see quite easily from the twisted matrix perspective that the bulk free energy and the free energy functionals have to obey these inequalities. This immediately implies that the free energy is a monotonically decreasing function of beta. We can also see this from thermodynamics, just by using the Helmholtz free energy and the first derivative with respect to temperature. Here, we show what happens with a particular maze when we change the temperature. We find the calculated free energy and plot it for several different betas. We see that indeed the free energy for this example is a monotonically decreasing function. Another relevant connection to thermodynamics is the Bogoliubov inequality. This inequality demonstrates how the free energy will change when the underlying energies in the problem are changed. This is a useful inequality when it is very difficult to calculate a partition function for some energy, we can change the energies to calculate an easier problem or solve an easier problem, which will then bound the true free energy. Using a similar construction, we can change the reward function to be some new reward function r prime, and doing this purely from linear algebra, we can show that the bulk free energy has to change in the same way that is specified by the well-known Bogoliubov inequality. This inequality states that the new free energy after the reward function has been transformed is bounded above by a function of known parameters, which all depend on this already solved reinforcement learning problem. The most important takeaway of this research is that the soft value function is just a non-equilibrium free energy. In the large n limit, this is simply a dominant eigenvalue and a dominant eigenvector for our tilted matrix. Moreover, we have established bridges between MaxEnt RL, linear algebra, and statistical mechanics. We've shown how linear algebra can influence solutions to MaxEnt RL. However, all of these bridges go both ways. Therefore, in future research, we will show how MaxEnt RL and statistical mechanics are more closely related, and how linear algebra and statistical mechanics can be influenced by MaxEnt RL. Thank you very much for coming to my talk, and please feel free to send me any questions you may have.